Hello. Last week we discussed the Born-Oppenheimer approximation, which invokes a perturbative expansion with respect to the ratio of the electronic to nuclear masses. Today we will go beyond the Born-Oppenheimer approximation and show that doing so leads to several very interesting ideas that are at the forefront of theoretical physics today. In 1951, Max Born re-examined the molecular problem without invoking the perturbative expansion and instead recasting it as an exact sum over states expansion. Thus, he expanded the total wave function psi instead of writing it as a simple product of an electronic wave function and a nuclear wave function. He expanded the total wave function in terms of the set of electronic wave functions psi I with the nuclear wave functions being the coefficients of expansion. Okay. Psi I is the electronic state wave function with the eigenvalues EI. Here the HE is the electronic Hamiltonian, and this electronic Schrodinger equation, as we saw, can be written in coordinate representation in this form. Okay. The electronic Hamiltonian, the HE, is a Hermitian operator, and therefore its eigenfunctions psi I form a complete set. Thus, the set of electronic wave functions psi I for all I now form a basis for the expansion of the total wave function psi. Using the exact sum over states expansion of the total wave function psi in the Schrodinger equation leads, after some algebra, to this equation here, where we have written the nuclear kinetic energy operator Tn as sigma alpha p alpha squared by 2m alpha, where p alpha equals minus IH cross del alpha are the nuclear momentum operators, and m alpha are the nuclear masses. The nuclear variables are represented by the Greek subscripts. Okay. Del alpha is therefore the operator for differentiation with respect to the nuclear coordinates. Note that the electronic wave functions psi j depend not only upon the electronic coordinate small r, but also upon the nuclear coordinates capital R. Therefore, we will have terms arising from operation of the nuclear momentum or the nuclear the derivative with respect to the nuclear coordinates of the electronic wave function. Okay. So, in addition to terms appearing in the Born-Oppenheimer approximation, we now have both diagonal and off-diagonal, that is J not equal to I terms, resulting from the action of the nuclear kinetic energy operator upon the electronic basis functions. These bond coupling terms take the form of a vector bond coupling Aij alpha, which arises from the matrix elements of the first derivative with respect to nuclear coordinates of the electronic wave functions, and a scalar coupling term Bij alpha, which arises from the second derivative with respect to the nuclear coordinates of the electronic wave functions. What the off-diagonal bond coupling terms Aij and Bij accomplish is that they serve to couple different electronic states I and J. The vector bond coupling term Aij appears in the equation of motion as a dot product with the nuclear momentum operator P alpha. Thus, we have Aij alpha dot P alpha. Okay. The Born-Oppenheimer approximation results from neglecting the terms involving the bond coupling terms. If you recall, the Born-Oppenheimer approximation has the nuclear kinetic energy, the electronic energy, and the internuclear repulsion energy. These two together form the potential energy surface upon which the nuclei move. Okay, so if we neglect the bond coupling terms, this gives us the total energy. Okay. The vector bond coupling term Aij can be rewritten as Aij alpha equals I times brass Ij del alpha of Vne psi I ket divided by Ei minus Ej. We see here the energy difference denominator. This means that if two electronic states come close to each other, or if they are degenerate, the bond coupling term blows up. Okay? The bond coupling terms becomes very large if the two electronic states come close to each other. If the two electronic states actually cross, then the bond coupling term goes to infinity. Okay? So the energy difference denominator indicates that a necessary but not sufficient condition for the validity of the Born-Oppenheimer approximation is that the electronic wave function must be non-degenerate at all points in the region of interest in nuclear configuration space. This analysis helps us to recast the molecular Hamiltonian into a gauge invariant form. It can be shown that the Aij matrix is Hermitian and that A plays the role of a gauge potential. And furthermore, that there is a relation between the B and the A. The B alpha is equal to minus half del alpha of A alpha plus A alpha dot A alpha. That is, Bij alpha is equal to minus a half del alpha dot Aij alpha plus sigma k Aik alpha dot Akj alpha. So that the molecular Hamiltonian can now be cast into the gauge invariant form. H is equal to sigma alpha 1 upon 2 m alpha times P alpha plus A alpha whole square plus EE of R plus VNE of R. Okay. P alpha and A alpha are the metrics of the nuclear momentum and the bond coupling matrix. E is the electronic energy, and VNN of course is the internuclear repulsion. Let us now examine the case of equilateral H3. The lowest molecular orbital is formed by the symmetric combination of the 1s orbitals on all three atoms. That is, psi 1 equals 1 upon root 3 1sa plus 1sb plus 1sc. The second molecular orbital is given by psi 2 equals 1 upon root 6 times 1sa minus twice 1sb plus 1sc, and that is degenerate with the third molecular orbital psi 3 equals 1 upon root 2 1sa minus 1sc. The molecular orbitals psi 2 and psi 3 are orthogonal to psi 1 and to each other, and as we saw, the psi 2 and psi 3 are also degenerate. Therefore, we can write the molecular orbital diagram as shown here. Psi 2 and psi 3, as we saw, are degenerate, and therefore the unpaired electron, the third electron, can occupy either molecular orbital psi 2 or molecular orbital psi 3. This degeneracy between the orbitals is split by a degenerate pair of vibrations which lead to distortion of the structure. Normal modes of vibration are eigenvectors of the nuclear Hamiltonian. The corresponding eigenvalues are the normal mode frequencies. The normal modes of H3 are given by the symmetric breathing mode Q0, where all three hydrogen atoms move out or move back in symmetrically, keeping the structure equilateral, and the degenerate Jahn-Teller vibrational modes Q1 and Q2. Q1 leads to a distortion from the equilateral to an isosceles structure, and Q2 also leads to a distortion of the structure. Q1 and Q2 are degenerate vibrations, and these lead to the lifting of the degeneracy between the orbitals psi 2 and psi 3. This shows the potential energy surface of H3 in the plane of the Jahn-Teller distortion coordinates Q1 and Q2. At the center of the plot is the equilateral geometry, which represents a maximum on the potential energy surface, and it actually takes the form of an inverted cone. Okay, so you can think of this as an inverted cone out here, and the Q1 and Q2 distortions lead to a lowering of the energy and a distortion of the molecule, and eventually to dissociation of the molecule along these channels into H2 plus H. Okay. This potential energy surface was computed in 1964 by my PhD advisor Richard Porter and Martin Karplus, who won the Nobel Prize for Chemistry in 2013. Porter, Stevens and Karplus showed that equilateral H3 is a simple example of a Jahn-Teller system. Okay. In 1937, Hermann Arthur Jahn and Edward Teller had formulated the Jahn-Teller theorem, which states that any nonlinear molecule with a spatially degenerate electronic state will undergo a geometrical distortion that removes that degeneracy, because the distortion lowers the electronic energy. The Jahn-Teller effect is an important mechanism of spontaneous symmetry breaking in molecules. It has far-reaching consequences in spectroscopy, stereochemistry, crystal chemistry, molecular and solid-state physics, and material science. Going beyond chemistry, spontaneous symmetry breaking of gauge fields is also at the heart of the standard model of particle physics. Jahn and Teller proved that in symmetric nonlinear polyatomic molecules, that is molecules with more than 2 atoms, with degenerate electronic states, the energy has to be linear to first order with respect to the displacement. That is, if you around the symmetric geometry to first order, the energy is linear. So this is like taking a cut through the cone. Okay, so the energy of the lower state or upper state is given by a linear term in the coordinate q, where q is any coordinate that breaks the symmetry, and thus the symmetric geometry is unstable. Hence, the degenerate point cannot be stationary, that is, the system is unstable against any asymmetric distortion which leads to symmetry lowering and a lowering in the energy. Okay. Thus, stability and degeneracy are mutually incompatible in nonlinear polyatomic molecules. A simple model of the Jahn-Teller effect is the Mexican hat potential energy surface, which takes this form here. And we see here, this is the Mexican hat, the bottom of this potential surface. The symmetric geometry is here, and here we see the 2 cones, one on top of each other. These 2 coordinates are the coordinates that break the symmetry and lift the degeneracy. For example, here the isosceles distortion breaks the symmetry of the equilateral geometry. Chiral symmetry breaking is an example of spontaneous symmetry breaking affecting the chiral symmetry of the strong interactions in quantum chromodynamics, which is the quantum field theory of strong interactions. We see here a parabola with a stable geometry at the center, a minimum at the center. If we distort this parabola, we get 2 minima. That's like taking a cut through the Mexican hat. And that leads to a lowering of the symmetry, and that lowering of the symmetry leads to an instability of the symmetric state and leads to a lowering of the energy. In the standard model of particle physics, spontaneous symmetry breaking of gauge symmetry associated with the electroweak force is also responsible for the separation between the electromagnetic and the weak forces. In 1963, Hertzberg and Longworth-Higgins predicted a change of sign of the electronic wave function when transported around a closed loop of structural deformations encircling a point of Jahn-Teller degeneracy between two electronic states. So the Jahn-Teller degeneracy is at the center, and this is the inverted cone. If we continuously change the molecular structure going around this loop, then the wave function will continuously change, but when we come back to the original point, the wave function will have changed sign. Okay. If the wave function of a given electronic state changes sign when transported adiabatically around a closed loop in nuclear configuration space, then that state must become degenerate with another at some point within the loop. This sign reversal condition is necessary and sufficient to establish the existence of an intersection. So Hertzberg and Longworth-Higgins showed that not only does is a sign change required, but this, when you transport the wave function around a Jahn-Teller intersection, but if the wave function change sign when transported around a closed loop, then that implies the existence of a Jahn-Teller intersection at some point within the loop. Okay. Of course, the total wave function has to be single valued. Okay. Therefore, this change of sign of the electronic wave function is compensated by a corresponding sign change in the nuclear wave function around the loop, leaving the total wave function single valued. In a regular loop, however much I rotate the loop, the arrows are always pointing up. They don't change sign. Whereas in a Mobius strip, now notice that the arrows are all parallel to each other. Okay, the arrows are all parallel to each other. However, as I rotate, as I go along the Mobius strip, I go from the upward pointing arrows to the downward pointing arrows. So a rotation changes the direction of the arrows from up to down, and I have to do one more rotation to come back to the upward pointing arrows. In 1979, Alden Mead and Don Trular identified the curl of the diagonal bond vector potential with a pseudomagnetic field. So if this is the double cone of the Jahn-Teller intersection, then one can imagine a pseudomagnetic field passing through that intersection. Now what happens if you traverse a closed loop around such a magnetic field? Well, we have seen the Aharonov-Bohm effect, which predicts interference between trajectories that pass on either side of such a magnetic field. Thus, Mead and Trular realized that the sign change predicted by Hertzberg and Longworth-Higgins is a molecular analog of the Aharonov-Bohm effect. And this is Don Trular on a trip we took in the Czech Republic. The molecular Aharonov-Bohm effect was experimentally confirmed by the group of Zwanziger and Ludger-Weste in sodium-3. Now, sodium-3 has a Mexican hat potential energy surface with 3 equivalent minima along the rim corresponding to the 3 isosceles configurations. So unlike H3, sodium-3 is not an unstable molecule. The stable geometries are the 3 isosceles configurations. And these 3 isosceles structures can interconvert between them through pseudo-rotation around the Jahn-Teller intersection. So what is pseudo-rotation? If you look at these isosceles triangles, it looks like they are the triangle is rotating, but actually this transformation is happening only purely through contraction of some bonds and elongation of some other bonds. So from here to here to here, and then back here, we come back to the original configuration. There is the pseudo rotation, and this was used by the group of Ludger-Weste to experimentally confirm the molecular Aharonov-Bohm effect in sodium-3. This is the pseudo rotation spectrum of sodium-3, and this is Ludger-Weste when he visited us at Shiv Nadar University in 2013. As we noted earlier, the Born-Oppenheimer approximation is valid only when the electronic wave function is non-degenerate at all points of interest in the nuclear configuration space. And this is because of the energy difference denominator in the expression for the bond for the vector bond coupling. And since the scalar bond coupling is related to the vector bond coupling, what happens when the energy difference denominator is small, that is when the electronic states come close to each other, the bond couplings become very large, and then it is no longer appropriate to neglect the bond coupling terms, and therefore the Born-Oppenheimer approximation breaks down when two potential energy curves or surfaces cross in energy or come close to crossing, that is an avoided crossing, as shown here in the transition state configuration. There is an avoided crossing between these two potential energy curves. In sodium chloride, we have an actual crossing of the potential energy curves. The ionic configuration is the more stable one. The covalent configuration is has a higher energy, but as we pull the sodium and the chlorine apart, the ionic configuration has a higher dissociation energy to sodium plus and chloride minus ions, whereas the neutral sodium and chlorine atoms lie lower in energy, and these two potential energy curves cross at this point, and at this point the Born-Oppenheimer approximation is expected to break down. Conical intersections are also important in biological systems. For example, in bacteriorhodopsin, which is a membrane protein from the Halobacterium halobium, and this illustrates how cells are able to convert the energy from photons into electrochemical energy. And a similar process happens also in vision. So this is the bacteriorhodopsin protein, and buried inside this protein is a molecule of retinal. Okay, this is shown in yellow. Retinal can undergo isomerization from the all-trans configuration shown here to the 13-cis configuration. So there is a cis-trans isomerization around this bond. Okay, and this isomerization from the all-trans to the cis takes place through a photochemical excitation and passage through the conical intersection. These are the potential energy surfaces of retinal. This is the all-trans configuration, and this is the 13-cis configuration, and the two are separated by a potential barrier, and there is a conical intersection here between these two surfaces. When all-trans retinal is photoexcited, it makes a transition to the upper electronic state, and then from there it passes through the conical intersection and comes down into the 13-cis form without emitting a photon. Okay. Thus, the absorption of light by retinal drives the isomerization of all-trans retinal to the 13-cis form through the potential surface intersection. And then the cis retinal undergoes spontaneous conversion back to the transretinal form, and then which can then absorb another photon, and the process continues. In 1984, Michael Berry showed that the Hertzsprung-Langevin phase and the molecular Aharonov-Bohm effect are manifestations of a more general phenomenon which he called the geometric phase. And this was also independently recognized by Barry Simon. In the general case, we have a Hamiltonian which has a parametric dependence on some parameter which can be varied in a loop. Okay. Well, this phenomenon was actually first observed in the field of optics by Pancharatnam in 1956 when he was studying interference produced by light waves in crystals. The Berry phase also has a classical analog, which is the Hannay angle, that is the change in the angle that a vector undergoes upon parallel transport around a closed loop on a curved surface. So this vector can be undergoes parallel transport, but when it comes back, it has changed its direction. And this is the change in the angle is related to the solid angle subtended by the loop at the center. And this is also the principle behind the Foucault pendulum. I will parallel transport this pencil on the surface of the sphere. I start out with the pencil pointing to the right, and at each point the pencil moves parallel to itself on the surface of the sphere. Go up to the North Pole and then come back. When I come back, the pencil is now pointing upwards. So the pencil is rotated 90 degrees. If I go all the way around, again start out with the pencil pointing to the right, go all the way around. Each point the pencil is moving parallel to itself, and when I come back, the pencil is now pointing to the left. So the pencil is rotated 180 degrees. So the angle of rotation of the pencil is proportional to the angle subtended at the center of the sphere by the loop that I have traversed. Let us now briefly discuss the modern theory of polarization. Recall the equation D equals epsilon 0 E plus P from electrostatics. In the modern theory of polarization, the macroscopic polarization P of a crystalline dielectric is related not to the charge distribution but to the Berry phase of the electronic wave function. This was pointed out by Raffaele Resta and by Richard Martin, King Smith, and David Vanderbilt. Although the macroscopic polarization has the dimensions of electric dipole moment per unit volume, we cannot define it as the dipole of the macroscopic crystal divided by its volume, since for a macroscopic finite crystal, the dipole has contributions from both surface and bulk regions, and these cannot be easily disentangled. Whereas for an infinite crystal, it depends on the shape and location of the unit cell. Thus, for instance, if we define the unit cell as this, we have a dipole pointing to the left. But if we define the unit cell as this instead, we have a dipole pointing to the right. So the average of P over all possible translational shifts is 0. The phase difference delta phi 12 between the wave function at 2 points r1 and r2 is given by minus the imaginary part of the logarithm of bra of psi at r1 times psi at r2 ket. And if we take points which are separated by an infinitesimal distance delta r apart, and we take a set of such points in a loop and let delta r go to 0, then gamma reduces to I times cyclic integral of bra psi of r del psi of r ket dot dr, which is just the Berry phase. This phase gamma cannot be expressed in terms of the eigenvalues of any operator. It is a gauge invariant phase of the state vector. Thus, although the Berry phase is a measurable quantity, it cannot be expressed as the eigenvalue or the expectation value of any operator. Thus, the Berry phase manifests itself in condensed matter physics as the macroscopic polarization of a crystalline dielectric at zero temperature and zero electric field. So the polarization is related to the integral of bra UNK del K UNK ket, where the UNK are the electronic block functions, which are the expansion of the total wave function in terms of a plane wave basis. And this is exemplified by the spontaneous polarization of a ferroelectric crystal. Now let us return to the H3 molecule. H3 with 3 electrons is an unpaired electron system. The ms equals half and ms equals minus half spin states are degenerate. That is, the third electron can have upspin or can have downspin. So the double cone that we have discussed is actually 2 double cones. Each of these is an alpha state and a beta state, and this degeneracy cannot be split except by applying a magnetic field. This is called the Kramer's degeneracy. The alpha and beta components of a Kramer's doublet are related by time reversal invariance. That is, T is an antilinear operator, which is called the time reversal operator, and T operating on alpha ket gives beta ket, and T operating on beta ket gives minus alpha ket. Okay. Alden Mead recognized in 1987 that the Born vector potential A alpha beta in the Kramer's degeneracy is an example of a non-Abelian gauge field. We will see more examples of non-Abelian gauge fields when we talk about the weak interactions and the standard model of particle physics. Finally, we should note that when we solve the electronic Schrödinger equation within the Born-Oppenheimer approximation, we normally give the coordinates of the nuclei as input parameters in the calculation. This led Woolley and Sutcliffe to ask, does molecular structure exist beyond the Born-Oppenheimer approximation? Is molecular structure really derivable from the first principles of quantum mechanics? To answer this question, I.L. Thomas in the early 70s performed calculations on second-row hydrides, such as water, ammonia, and so forth, putting electrons into electronic orbitals and protons into protonic orbitals, and antisymmetrizing the electrons and the protons separately. No nuclear coordinates were provided as input parameters for computing the eigenfunctions of the total molecular Hamiltonian. Only the numbers of each kind of particles, that is the number of electrons and the number of protons, were supplied as input. The picture that emerged here is that equilibrium bond lengths and bond angles appeared as peaks in the protonic radial distribution function. Thus, just as the Bohr radius appears in hydrogen as the peak in the electronic radial distribution function, here the bond lengths and bond angles appear as peaks in the protonic radial distribution function. These computations yielded a remarkable structure for ammonia, very different from the expected pyramidal structure. The molecular structure of ammonia beyond the Born-Oppenheimer approximation is now a disk centered on the nitrogen atom. So normally in the conventional Born-Oppenheimer approximation, ammonia is described as a pyramidal structure, and it can be an upward pointing pyramid or a downward pointing pyramid. And in the Born-Oppenheimer picture, we talk about the umbrella flipping between the upward and the downward pointing pyramids, whereas in I.L. Thomas's calculations, the ground state of the total molecular Hamiltonian, that is psi plus, was a linear combination of psi 1 and psi 2, a symmetric linear combination of psi 1 and psi 2, which gave a disk-like structure. And the first excited state was the antisymmetric linear combination of psi 1 and psi 2, and the difference between the energies of these two states corresponded exactly with the experimental microwave transition frequency in ammonia. While the pyramidal structure of ammonia is indeed the equilibrium ground state structure obtained from solution of the electronic Schrödinger equation within the Born-Oppenheimer approximation, it is not an eigenfunction of the total Hamiltonian of the isolated molecule. The ground state solution of the total molecular Schrödinger equation beyond the Born-Oppenheimer approximation is a symmetric linear combination of two pyramidal ammonia wave functions psi 1 and psi 2. The wave function of the first excited state psi minus is the corresponding antisymmetric linear combination. Excitation of a proton from psi plus to psi minus gives rise to a line in the protonic spectrum that corresponds to the observed microwave line in ammonia, which is conventionally explained as due to the umbrella flipping transition between psi 1 and psi 2. We will stop here, and we are approximately midway through this video series. And in the next episode, we will return to the historical narrative and more philosophical considerations.